Swayam Prabha. Digital India. Educated India.
Okay, in the previous class, we defined this quantity called the tangent cone. Okay, so the tangent cone, remember how the tangent cone was defined for two things. One is a set S, and say a point x star that lies in the set. So, for example, if this is point x star and this is your set S, then the tangent cone T of x star with respect to x was defined as those directions D by which it is possible to approach the point x star from within the set S. Okay. So, tangent cone is those D's such that there exists a sequence xk that lives in the set S, xk converging to x star, and a tau k that decreases to 0 such that D can be written as this limit xk minus x star divided by tau k. Okay. So, what we learnt was that if you look at this sort of sequence that is eventually converging to x star. So, here is my point x star suppose, and this is my sequence that is it dances around all over and then eventually gets converges to x star. Then this ratio limit as k tends to infinity xk minus x star divided by tau k, this ratio is actually capturing the tangent to the trajectory of the xk's. As xk goes to x star, this is the tangent to the trajectory, and my intuition for that that I explained was that you should think of xk minus x star as the distance between xk and x star, and tau k as a unit of time. So, this is like a velocity, right? It is the rate at which xk is approaching x star. So, it will eventually become tangent to the precise curve that x star trajectory that xk traces. All right. So, these were the this is, you can think of the tangent cone as the limiting directions through which it is possible to approach x star from within S. Okay. And what was the significance of this tangent cone? The significance of this tangent cone was that it captured a very general necessary condition for optimization. So, if you have a general function f, just that f has to be differentiable. So, let us take continuously differentiable, and x, and you are minimizing this function f over all x in a set S. S can be any kind of set, can be a polyhedron, can be not a polyhedron, can be convex, not convex, does not matter, any set S, and you are optimizing of an arbitrary differentiable function over it, then we had this result that x star, if x star is a local minimum of this optimization, problem, then it must be the case that the gradient of f at x star makes an acute angle with all vectors d that lie in the tangent cone at x star with respect to S. So, this is an extremely sweeping and general condition, and it is probably the most general condition known to us about that captures a necessary condition for a point to be a local minimum. Unfortunately, there are, just for you to know, this is not actually sufficient. So, note that even though this is the most general condition, it is not in general sufficient. Okay, there are counter examples that of where you have a function that is where you have of a function and a set where this condition is satisfied. That means this condition here, the underlying condition is satisfied, but the point x star is still not a local minimum. Okay, so it is not sufficient. There are so this condition may be satisfied, point x, but the point x star may not be a local minimum. All right. The other thing we saw about the tangent cone was that the tangent cone is actually a treacherous object. Means that you might think that if you have suppose two sets S1, S2 and a point x star that lies in both S1 and S2, and if you wanted to find the tangent cone with respect to the set S1 intersection S2 at x star, then this is not in general this set. So, it is not in general, you cannot construct it by simply taking the tangent cone of the point S star with respect to S1 and with respect to S2 and then taking the common region of the other two. If you do this, you would in general get a much larger set. So, this is, so the intersection is actually just a subset of this larger set. Okay. So, but still having said that, this turns out to be it turns out that in optimization this is still our best bet. What we, so the way optimization theory proceeds is that it tries to put conditions to make this equal. Okay. So, we conditions to somehow make this equal, and that is what I will try to discuss today. Okay. So, so for this let's go back to optimization, the form of an optimization problem. So, now instead of taking an arbitrary set S and an arbitrary function like this, we will describe the set in a much more specific way. So, we will now write the set using its constraints. So, consider now an optimization problem of the following kind. You are minimizing a function f subject to constraints that look like this: g I of x less than equal to 0, where I goes from 1 to m. So, you will notice that I have not used equality constraints here, and that is for a reason. I will bring those equality constraints in subsequently, but for the moment let's focus on this particular type of optimization problem, right. So, here you have f of x as the objective, and g I of x is from I equal to 1 to m. These are your m constraints. Each g I is, and f itself, they are all functions from R n to R. Okay. So, each g I of x is a scalar function, and we will assume that they are all continuously differentiable. Let us assume that they are all continuously differentiable. Okay. So, now what we will do is we will see if we can somehow get to an understanding of the tangent cone of this particular set. Okay. So, we know that if you so this here, the feasible region now S, which is x such that g I of x less than equal to 0 for all I from 1 to m. This is nothing but the intersection of these regions. It is the intersection of these individual sets. Let us call these SI. right. So, if I want to know what the tangent cone at a point x star in S is, then that amount I can try to see if I can get to this by looking at the tangent cone of x star with respect to each of these SIs, right. And the hope is that this would turn out to be the same as the intersection of all of these. Now, we know that this is in general not true, okay, but we will try to see when we can make this work. Okay. All right. So, now let's do a few simple things. Now, if you have what is a constraint like this g I of x less than equal to 0, if I have a constraint like this where g is a continuously differentiable function, what does that constraint look like? So, that constraint, if you see here's a region that constraint describes. So, the boundary here of this region is say g I of x equals 0. The interior here is g I of x strictly less than 0. So, if you have a point x star that lies here in the interior of this, for such a point g I of x star must be strictly less than 0. So, here that must be the case. So, it is a point it's a point for which g I of x star is strictly less than 0. So, for this sort of point, what would be the tangent cone with respect to SI? Now, this sort of point lies in the interior of the set, and we had seen this last time, that if you have a point that lies in the interior of the set, then the tangent cone is the entire space, right. So, you can approach the point from every possible direction in the ambient space, right. So, consequently, for such a point, you must have that the tangent cone is actually Rn. So, so what this means is, so if out of these sets or out of these constraints G1 to Gm, if any of them are satisfied with strict equality at x star, then they do not, the tangent cone with respect to those sets will not appear in this intersection, because the tangent cone there is just Rn, right. So, this here is therefore can be written in the following way. You can write this as the intersection over I in a set A of x star, and I will define what A of x star is, where A of x star is nothing but those i's for which g I of x star is exactly equal to 0, because once g I of x star is strictly less than 0, the tangent cone is Rn and it plays no role in the intersection, right. So, in other words, when I have to try to describe my the tangent cone with respect to my full set, what I have now brought the problem down to just this one part, which is that I need to now describe the tangent cone with respect to the set Si, right. So, I need to with respect to the set Si for those i's that lie in the set A of x star. A of x star is what is called the active set. Yes. Yeah. So, T of x star with respect to S is okay. We are hoping that this can be somehow made equal to this intersection here, right. I am hoping that this can be made equal to this intersection, but then in this intersection, if I look at those i's for which g I of x star is, so if I look at an I for which say g I of x star is strictly less than 0, then such an x star will lie in the interior, right, and then for around that x star I can fit a ball, and also that will lie completely in the set. So, the tangent cone with respect to that particular set Si would be Rn, right, at the point x star. So, that is why when I look at this intersection here, those i's, the i's for which gi of x star is strictly less than 0 will not count in this intersection, because they are all Rn, right. So, what will remain is only the i's for which gi of x star is exactly equal to 0, okay. And those are what we call that's the set of such i's, they are called the active set, or the i's are themselves called the active constraints. So, we say that a constraint is active. So, a constraint is said to be active if the at a particular point, okay, we say the constraint I is active at x star if gi of x star equals 0. Now, to be the active set, okay, remember, is a function of, will change with x star. At a point x star, at this point the active set will be the constraint that I have drawn here, it is not in the active set, okay. And maybe another constraint like this may be in the active set here, this sort of constraint. This is in the active set, because it x star lies on the boundary. So, if I take this sort of constraint here, this is in the active set, okay. But if I if I change my point x star to this point here, suppose if I take this as my point x star, then this constraint will now become active. My earlier one, which was not active earlier, will now become active, whereas whereas this one will not be active anymore. The green one will not be active anymore, right. So, which constraints are active really depends on the point x star, okay. Certain constraints may be active, certain constraints may be inactive, etc. But the point is, once I give you the x star, I know immediately which constraints are active, and if I have to look at the tangent cones, then all I have to do is focus on the tangent cones of those individual constraints, all right. Okay. Now, let us look at one of these individual constraints now. Let us see if we can make sense of the tangent cone of any of these individual constraints when they are active, okay. So, let us see, suppose I have a constraint like this. Let's for simplicity, let me just change the direction for the moment. I will just write this as a greater than equal to 0, because that's easier to explain, okay. So, suppose we have a gi of x greater than equal to 0 is my constraint, okay. Now, if I look at what we are tempted to think is that, well, the tangent cone, and because g is continuously differentiable, what we are tempted to think is that, well, I can capture the tangent by looking at the gradient of the function gi, right. So, I am looking at a point x star which is on the boundary, okay. So, what I need to do, geometrically what I need to do is look at all these directions by which I can approach the point x star, all of these directions, and eventually all the way till I get to the tangent surface, the surface that is tangent to this constraint at x star, all right. So, this is because I have written it as a greater than equal to, I have this gi of this region is gi of x strictly positive, this boundary is gi of x equals 0, and so on. So, what I want to do is to get to this tangent. So, geometrically this is actually correct. The trouble is, how do I get a formula for this? Means I have the right geometric picture here. Yes, I need a tangent and so on, but what is the formula for the tangent, and how do I express that tangent using the function g. Now, if I drew a circle, for example, here, you would know how to draw the tangent. Well, you would know what the tangent is, and you would know what the formula for that tangent also is. Well, what do I need to do? I need to look at the gradient here. The gradient will be pointing is going to be a normal. Look at the normal, direction should be in the direction of increase of the function. Okay, that is where the gradient will point, and then using that, perpendicular to that would be my tangent, right. The space that is whose normal is this particular gradient would be my tangent. Okay. So, let us see if we follow through on this, what you would think would be, how would you capture this particular space? Well, it would be the space that is perpendicular to the gradient at this point. Okay. And now, where would the gradient at x star point? See, so this region here has gi of x strictly positive, and as you get to the boundary, gi of x has become 0. The gradient should be pointing in the direction of increase of the function, right. So, the gradient of gi at x star will be normal to this boundary and pointing inwards, right. So, this is where you would think, this is where the gradient would be. So, this here would be gradient of gi at x star. So, and then you would think that, well, what would be this space then? What would be the tangent cone in that case? Well, you would think that the tangent cone will be those d's that make such that gradient of gi of x star transpose d is greater than equal to 0, right. So, it is all these directions d which make a acute angle with this gradient. So, all of these directions up till the point where you become tangent. All of these directions are, you would think, are in the tangent cone. No. So, unfortunately, the convention of the tangent cone is that it centers it at x star. So, it is xk minus x star. So, the origin has been shifted to x star. So, it is always origin from x star towards xk. Okay. So, that is how you define the tangent cone. Yeah, that is unfortunately, that is been the convention, although I mean, it is easier to explain it as the directions by which you can approach, but it seems like you are heading towards x star, but actually if you see, it is the other way around. Okay. All right. So, this is what you would guess would be the tangent cone at a point x star. So, what is this? So, just to summarize this, you have a point x star such that gi of x star is equal to 0, and you would think that for such a point, the tangent cone would be equal to this. This is what you would think, but the trouble is, this also is not true. So, if a simple case like this, where you have a point x star which is on the boundary, you have a differentiable function, you know what the normal is, you can calculate the normal and so on, and you would yes, you would think that, well, the tangent cone should be equal to this. The problem is that also is not true, and the reason for that is this simple problem, which is the following. So, this constraint, if I look at this constraint gi of x greater than equal to 0, right, this constraint is actually the same. Okay. So, if this constraint is actually the same as the constraint gi of x the whole squared is greater than equal to 0. Okay. So, or more specifically, we can even, it is probably easier to see this in the case of an equality constraint. So, maybe let us do this for an equality constraint, and I will be able to convince you more easily. So, Suppose, so this was for the case of a greater than equal to constraint. Suppose if I had a surface like this, if I had a equality constraint, suppose I had a surface h of x equal to 0 and I took a point x star on this surface, you would think that the tangent to this would be something like this. This would be the direction of the gradient of h at x star, and you would think that the tangent cone with respect to that sort of set would be d such that gradient of h at x star transpose d would be equal to 0, right, almost following the same sort of reasoning as before. The trouble is, this is where the it starts begins to break down, because h of x equal to 0 is equivalent to h square of x equal to 0, and h square of x, which is equivalent further to any, say h cube of x equal to 0, and so on. I can keep taking powers of x and I will continue to get the same set. And so what is the reason for this? The reason for this is this h of x equals 0 is the same as, any power of h of x also equal to 0. But then what is the problem that this creates? The problem is that, yes, I am looking, if I look at the gradient of h of x, okay, for the same set, I apply this particular formula. On the one hand, I will get gradient of h. On the other hand, I will get something like this. I will get 2 h of x gradient of h. And what is h of x at that point? 0, which is equal to 0. If I apply it for this one, I will get 3 h square, again gradient of it. You see the problem that has occurred. The problem is that the same set of points, geometrically the same set of points, can be represented in multiple ways using algebraic constraints. And when we say we know the formula for a normal and so on, all of that presumes something about about how we have represented the constraints algebraically, right. So surely it can, this is not fair, right, this is not acceptable, that the same set will end up having multiple will have very different formulae based on how you have chosen to represent it, right. So this is the trouble. So the trouble, where is the challenge? What is the reason for the problem? The reason for the problem is that basically there is a gap between the way the optimization is proposed as a geometric problem, as a set of points over which you want to optimize, versus how you want to represent those geometric points using constraints, right. So the representation is it's what's coming in the way here. But how do we know what is the original h of x? But how do you know that it cannot be reduced further? See, the point is that there is the geometric normal is not necessarily, the issue is exactly this, the geometric normal is not necessarily the gradient. The gradient, it could be 0, even though there is actually a normal to that set. Geometrically, there is actually a normal to that set. And there is, how will we know what the actual normal is from the formula, right. So what I wanted to illustrate in this was that there are basically multiple ways by which you can represent the same geometry.